Okay, ladies and gentlemen, let me see if we can get the audio working. Apparently you can hear me, also in the back. Excellent. Welcome to this short session about flexible power generation based on reciprocating engines. This was a presentation based on a paper that we held this morning, and I'll run it through to you. What we'll talk about in a few minutes here is the amount of variable generation that you will see in the grids coming up. And it actually doesn't matter which kind of roadmap you look into, you see that there will be a lot of variable generation coming into the future grids. If we, for instance, look at these graphs here, and I will make them a little bit easier to read for you, because what you need to focus on is the part of Europe today belonging of 7 to 8% of renewable energy based on wind and solar. And in 2030, we see that according to these prospects, it would be in the region of 30%. So you see a big increase in renewable generation. And here you have then a bit of a challenge to be able to cope with this. You need a lot more variable generation, because the wind and the solar, they have a natural volatility. That's something that you just have to cope with. You have the predictability, and you can increase in the predictability, but there will still be an error in the forecasting, for instance, of wind. And then you may also have some restrictions with dispatchability of wind and solar. You actually have to dispatch them when you have wind and sun, so that's quite easy. Now, if we have a look at how the future grid would look with the 2020 scenario set by the European Commission, we see that on a low wind day, you have a lot of flexible capacity need. And if I'll guide you through a day with average wind, you see more wind, and you see a lot more ramping up and ramping down by the flexible capacity, which is with the orange color here. In a high wind day, then again, you may even be in the position that you have to do frequent daily starts and stops. And it may not be just 2 or 3 daily starts and stops that we see over here. It may be 3, 4, 5 daily starts and stops that you see by the flexible power generation. If we then look at how can you cope with these challenges, now there are some factors to consider, and I will not mention all of these here, but regarding the solutions that you have to think about, one is of course to have regulation by conventional generation, meaning more or less the thermal power plants, and have them to act faster. The other thing would be to have some kind of buffering energy storage, which is one option as well. However, still not a mature technique, and you also need to think about the cycle efficiency, because what you put in the storage, you also have to generate out of the storage. And there you will have some losses of total efficiency. Then number 3 is more about demand control, and one way of putting that would maybe be also the smart grid discussion that you will hear from Mikko in a short while. But that may also not be the whole truth how to cope with these challenges, because today we are used to have electricity when we want, we are used to use the dishwasher when we can, and will we be able to understand and accept that people will control this for you? That may be a little bit difficult thing that we need to learn to cope with. We think that our technique, the reciprocating gas engines, have a number of benefits, a number of advantages that we can utilize for the flexible power needs that we see. We have listed a couple of them here. For instance, the highest simple cycle efficiency of about 46%. We have the flexi-cycle, combined cycle solution that you can see on display also there by the nice animation. There is a really high efficiency in hot and dry conditions. You have stepwise expandability, and then you have a high load range, high efficiency over the wide load range with the solution. If you then look at the operational excellence part of this, you have the more or less unlimited, fast, reliable starting and stopping. Cyclic operation is not a problem. You have fast results, fast ramping, and you can see that you have a firm capacity that you can rely on, the double capacity. Regarding the point number 3 of this smart power generation program, the super flexibility. Number 1 is that the gas that we use is a low pressure gas, 5 to 6 bars only. And also operate molecules, and there is also a rule of flexibility. This graph shows an example of the load efficiencies over the whole plant efficiency over the whole load range. And you can see in an example here of, let's say, 10 times 18 megawatt power plant. And when you follow the curve, you can see that we maintain a high efficiency even though we would take down some of the engines, stop some of the engines. And actually, it is down to a level of 10% of the total plant load, and we still maintain an efficiency which is high above 45%. And this stepwise operation is a true benefit that you don't find by any other technique. So this multiple generating set operation is one of the major benefits that you can have. Then, when you think about wind dropping off or coming into the picture, you need to react really, really fast. And we are quite proud to have a solution which can synchronize within 1 minute and reach full load within 5 minutes. So loading is done under 4 minutes only. This is of course excellent. The beauty here again is the multiple engine perspective and solution, where you can have either one unit at 9.7 megawatt or 20 units at close to 200 megawatt. And it's the same 5 minutes for all these different solutions for the power needs. 10 megawatt, 100 megawatt or 200 megawatt. Now, then you also have to react fast when you have an excess of wind. And then we talk about the unloading, which is also extremely fast. Within 1 minute we can drop the whole load. And of course, we can load back again at any point here in the curve. But if needed, we can stop, and then after just a few minutes, we can start and load back again. How is all of this possible? It's possible because that we utilize a technique which is not so much focused, or let's say depending on the temperatures. It's not that high temperatures that we're utilizing, so the components will not suffer from this kind of operation, but also the future, let's say the modern control systems of the engines today, based on embedded controllers, high-speed processing, high-speed data communication, and cylinder-wise control on each cylinder, based on closed-loop control, where you measure the fuel pressure in the cylinder and control the fuel supply accurately according to the lowest emissions and the highest efficiency. This is part of the reason why this is possible. This is a true case example of how we stabilize the grid. This is from HG Energy Power Plant in Turkey, recently commissioned just 6 months ago. And this consists of 6 times 9.7 megawatt generating sets, and the total power plant output is 52.4 megawatts. Now, what is interesting in this picture is that the upper curve is simulated system frequency drops of 0.2 hertz plus and minus, and the lower curve is then the reaction of the generating set, which we have to test in order to comply with the local TSO TEJAS in Turkey. Now, the interesting thing here is that you can see on the green curve an incredibly stable operation, really fast reactions, and this is not our manipulated data by any means. These are reports from TEJAS, and it is with a 100 millisecond sample time. And it's also unfiltered data, so it's really the real thing and real operation. Regarding the stepwise extension possibility, I think this is a good picture showing the possibility to have a just-in-time investment. You can start with a 30 megawatt solution, then depending if the demand grows, you can invest in more, and it's easy to expand. And this is really supported with the solution. And this brings me to the conclusions before I hand over to Mikko. And we really think that the smart power generation solution is needed. There will be the book here for you to pick up later on. With this, you can have the highest efficiency, the best flexibility, firm capacity. You have the modular power plant, which enables positioning really close to the demand in the so-called load pockets. And we really think that the modern reciprocating engines, they do have the needed capabilities for supporting the future grids for years to come, and will thus enable wind, solar and other renewables coming into the picture. That, ladies and gentlemen, concludes my presentation. Thank you very much for the attention, and please remember to take some books after Niklas' presentation. Thank you very much.